Welcome, my dear students. Today we are going to discuss about the robot dynamics and control. Actually, last few classes we have been concentrate on robo kinematics and dynamics. In the dynamics, already discussed about the mathematical model of robo by means of Lagrange's principle, okay, Lagrange's method. Okay, so in continuation to that, we are moving towards control. Okay, we modeled the general dynamic equation for the robo manipulator. Actually, what is the dynamics of a general coordinate for two-link manipulator? So the dynamic equation of say general manipulator link. Okay, say we normally discuss with the two-link manipulator only, two-link, say RR manipulator, two-link manipulator, two-link manipulator. What is the generalized? We devised the mathematical model of two RR robo. I requested you to model a three-dimensional robo, that is 3 degree of freedom robo, RRR. But nobody replied for that. Okay. So anyway, the mathematical dynamic equation of a generalized coordinate robo is nothing but m of q double dot. Actually, q is the link coordinates. In some cases, we can represent q. In some other times, we can represent as a theta. Theta is the mostly the joint parameters, right? So m of q with respect to q double dot, then c, sometimes c or b, sometimes v or sometimes v. So many representations are there. So c of q comma q dot plus g of q plus f of q dot equal to tau. This we have been devised in the last lecture. I represented the dynamic equations for what is m of q, q double dot. Then we can remove this, no problem. M of q, q double dot, c of q comma q dot, g of q plus f of q dot equal to tau. What are where q? What is q? Q is the joint parameter. All are n by 1 vector, n cross 1 vector. Q dot, q double dot, q dot, q double dot. Or this is all displacement, the joint displacement, joint parameter. Q dot is velocity of the joint. Q double dot acceleration of the joint. Velocity of the joint. Okay. So all are n cross 1 vector matrix, right? N cross 1 vector, where tau is the n by n cross 1 vector is a input torque. So this is input torque. Okay. Then m of This is so n by n cross 1 vector m of q dot m of q double dot, that is m of q is the n cross n symmetric matrix, symmetric positive definite manipulator inertia matrix. Okay. How do you define this? M of q, this is nothing but n cross n symmetric positive definite manipulator inertia matrix. Okay. So what is C of Q? C of Q, comma Q dot is n cross n centripetal force. Okay. That is Q of n cross n centripetal and Coriolis. Okay. Coriolis top. Then G of Q is a gravitational force represented by n n cross 1 vector, n cross 1 vector. Okay, actually this can be obtained by the gradient. Okay, gradient of the robo potential energy due to gravity. So this can be obtained as the gradient of the robo potential energy. Okay, potential energy due to gravity. Then F of Q dot is the friction torques. So n cross 1 vector. Okay, the matrix C of Q and M of Q, the matrix, this matrix C of Q comma Q dot and M of Q are the inertia matrix which should satisfy the time derivative, the matrix C of Q and the time derivative of M of Q at the matrix, inertial matrix, such that it should satisfy this condition. What is the condition? It should satisfy Q dot transfers 1 by 2 M of Q minus C of Q comma Q dot into Q dot should be equal to 0. So the matrices C of matrix C of Q comma Q dot and the time derivative of M of Q of the inertia of the inertial matrix should satisfy the above condition. This is the very important relation that for the controller design. So we are going to design P controller, PA controller, PID, PD controller. So computational torque controller. There are many controllers that are. So we are going to design those controller. For all the controller, this equation, this dynamic equation is the very important relation. Okay. Again, we consider the 2 degree of freedom manipulator arm. Okay, so theta 1, theta 2, this is the P end effector, Y, this is X. Okay, so let M1 and M2 are the masses of arm 1 and arm 2. Say, let M1 and M2 are the masses of the joint. Okay, masses of the joint or arm, masses of the or the masses of arms 1 and 2. Similarly, L1, L2, L3, L1, L2 are arm length, link length respectively. Similarly, tau 1 and tau 2 are driven torques. Tau 1 and tau 2 are the driven torque. For arm 1, for arm 1 and 2 respectively. For all respectively, right? Similarly, Q1 and Q2 are the positions of the arms, 1 and 2. Right? So, as per the dynamics model given above, the dynamic model of the two-link manipulator, the dynamic model of the two-link manipulator for this diagram, that is, this is L1, this is L2, can have the center of gravity point for both this. Say M1 and M2 are the masses of the two-link manipulator. What is Q? Positions of the Q? Actually, here Q1 is theta 1, Q2 is theta 2. Am I right? So Q1 and Q2 are theta 1 and theta 2. So what is Q? Q is, you can write either theta or Q, right? I am going to follow Q1 and Q2 transpose. What is Q dot? Q dot equal to Q1 dot Q2 dot transpose. Okay, so then acceleration, this is velocity, this is position, this is velocity, this is acceleration. What is acceleration? That also same, Q1 dot Q2 dot double dot, sorry, transpose. So what is tau driven torque? Tau 1 comma tau 2 transpose. Okay. So the M, the parameters M, then B or C, the velocity, right? M, comma B, comma G can be described as, what is M of Q? Last class itself, we have discussed these matrices. So what is M of Q? M of Q equal to M1 L1 square, M1 L1 square plus M2 of L1 square plus L2 square plus 2 L1 L2 cos theta 2. Okay. Another element is M2 L2 square plus M2 L1 L2 cos theta 2, cos theta 2. Okay. Then M2 square, M2 L2 square plus M2 L1 L2 cos theta 2 equal to M2 L2 square. So this is the matrix, inertial matrix M of Q. Okay. So then C of Q, C of Q, C of Q, comma Q dot equal to minus M2 L1 L2 sine theta 2 Q dot square, Q dot square minus 2M1 L1 L2 sine theta 2 Q1 dot Q2 dot then second is M2 L1. Actually C of Q is N by 1. C of Q is N by N side centimeter for this process. M2 L1 L2 sine theta 2 Q1 dot square. Okay, this is C of Q. Then G of Q, due to gravitational force, M2 L2 G cos theta 2 G cos theta 1 and theta 2 plus M1 M2 to G L1 G cos theta 1 M2 L2 G cos theta 2. This is the matrix G of Q, right? G of Q. If we substitute the values of M, say I'm going to make assumptions that M equal to M1 equal to 10 kg. The link arm link weight, arm 1 weight is 10 kg. Arm 2 is say M2 equal to 3 kg. Length, arm length link 1 equal to say 1 meter. Similarly, L2 equal to 0.8 meter. So these are all constant parameters of the two-link manipulator. So let us substitute these M1, M2 values in these expressions. We will get the force or torque F of Q equal to 3Q dot Q1 dot plus 0.5 sine theta 1 dot 2Q2 dot 2Q2 dot plus 0.5 sine say theta 2 dot. Similarly, the torque TD, torque disturbances, like Q, comma Q dot equal to 5 cos theta 1, 5 cos theta 2. Now, these are all the numerical values of the two-link manipulator model equations, model dynamic equations. Now, I am going to introduce a new concept called Jacobian equations, Jacobian approach for the dynamic matrix. So, the Jacobian approach is useful for determining the forward kinematics as well as reverse kinematics solution using the dynamic equations. We already discussed, let us see, we already discussed Jacobian method. We already found the solutions of forward and the reverse kinematics using geometric approach and as well as the algebraic approach. Okay, so this method introduces the determination of forward the linked parameters using the dynamic equations. Using the dynamic, this is a dynamic approach. This is a numerical. This is a numerical approach. Numerical approach, right? So it introduces the Jacobian parameters J equal to dou x by dou q. So what is x? X is the parameter in universal, dou x, dou y, dou z. Okay, with respect to dou q. So in this dou q can be approximately equal to Jacobian inverse of dou x. Okay, dou x or del x, dou q. So dou x by dou q equal to this approaches, we can determine the parameters q dot, that is theta 1, theta 2, etc. from the Jacobian inverse. First, actually, what is Jacobian? So Jacobian is the matrix which is nothing but differentiation of the parameter, the world space coordinate. This is world space coordinate. This is joint space coordinate. So first we have to differentiate dou x by dou q. So from this we can obtain easily the Jacobian matrix. Okay. So singularities. So mainly this is for particular singular positions. The singularity, the world space of the manipulator is very important. There will be some poses. Okay, poses on the manipulators, the end effector, right? Singularities also occur when manipulator loses a degree of freedom. When it loses a degree of freedom, when the joint is not movable one. So when the joint is static, so like this, okay, it is not moving. So when the joint is static, it is in a straight, like say. So this is a joint, this joint parameter. Okay. So when singular, according to the numerical approach, when the forces will, there will be any loss in the loss of control when the joints are aligned in a straight line. So when the joints are aligned in a straight line, uh, the for this condition, determinant of the Jacobian matrix will be equal to 0. So when there is loss of control in the force, then the determinant of the Jacobian matrix will be 0. Okay. So what is velocity in the dynamics equation? Velocity of the dynamic equation is can be represented like n with respect to the end effector, p with respect to the position. Okay, actually we can specify the velocity of a position of a point in the frame, say of a point in the frame. So we can represent the point in the frame with respect to another relative frame. So suppose this is the point. We can specify the point using either world space coordinate y and x, or with a particular point on the space. So we can represent this point of a frame with another frame. So with respect to the another frame also we can represent. Okay, so this is the equation for velocity of a point with respect to another frame. This can be written as point with respect to A and B plus rotational matrix. We already discussed this concept into BP. So a velocity of a point A can be represented as velocity of A with respect to B plus rotational matrix R A with respect to B into the point lies on the another frame B, right? So then this can be rewritten as velocity. This is velocity of A of a point B equal to B, BO or G A plus A, or this is a rotational matrix A with respect to B, then velocity B with respect to point P plus the omega A with this angular velocity into A R B into PB. So this can be represented as the velocity relation. So what it tells is there is a skew symmetric matrix. This is a skew symmetric matrix. Symmetric matrix. So what is velocity? Velocity, the linear velocity is nothing but angular velocity into r. So this is the velocity expression. Velocity, linear velocity is angular velocity into r. Similarly, the omega matrix can be represented as 0 minus omega in z direction, omega in y direction, omega in z direction, 0 minus omega x direction, minus omega y direction, omega x 0. So this is the matrix for omega. So V equal to this omega into r, V into omega into r. Sorry. Omega into r. So the angular velocity can be represented from one point to another point. Let us see. from this point. This omega delta t. So the angular velocity passes through the point P near rotational velocity, right? So this is the angular velocity with respect to body B. This is theta. This is point P of t. This is the point t plus del t after a change. So this is P. This is del P. P of t, etc. Right. So for a small instant, we are taking the time, small time. Here, yes, a small time. Here you see. For the small change in time, so we are taking the small segment from the angular velocity. So if we look at a small time slice as a frame, rotates with a rotating moving point. Okay, so that can be written as modulus of p, the change in position, modulus of a p sine theta. So this can be a p sine theta. Actually, this is the theta. This is a p sine theta. This because this is an opposite side. Sine theta into a b into this is modulus into del t. Similarly, for del p by del t for the instant, small instant, so we can write as a p sine theta. Only if you bring this theta del t to here, then it becomes a angular velocity v. So this can be written as angular velocity of point with respect to b into p a into p a. So hence velocity of a point p with respect to the frame a is nothing but angular velocity of a with respect to b with respect to a into rotational velocity of b with respect to a into the point p with respect to the another frame b. Clear? So this is about the angular velocity. Then representation of angular velocity. How to represent angular velocity? Velocity representation. Velocity representation. So for we already have the rotational matrix when the frame rotates about x axis with an angle of alpha, beta, gamma, like that we studied, right? So for x, y, z. Okay. So what is there? Alpha, beta, gamma. So this already we obtained. So rotational matrix of x about alpha and rotational matrix Y comma beta. Similarly, rotational matrix Z rotational matrix Z comma gamma. So this can be written as a matrix alpha dot velocity matrix rotational beta and gamma, right? Minus sine beta 0 1 cos beta into sine alpha cos cos gamma alpha cos sine alpha cos alpha 0, then cos beta sine alpha minus sine beta 0 into omega x omega y omega z, right? So omega z. So this is the velocity representation for the frames, rotational frames r, rx, ry, rz, right? So the uh, uh, quaternion, okay, the quaternion, the input, the individual parameters of the joint, okay, that is called the quaternion, right? Quaternions. So what are quaternions? So at the sigma, so epsilon 0, epsilon 1 dot, epsilon 2 dot, epsilon 3 dot. This can be written as 1 by 2 of epsilon 1 minus epsilon 2 minus epsilon 3. So epsilon naught, epsilon 3 and minus epsilon 2. Then epsilon 2 minus epsilon 1, then epsilon naught into angular velocity omega x, omega y, omega z. So what is then manipulator velocity? Okay, manipulator velocity. Manipulator velocity. Velocities. So consider the schematic of the planar manipulator. Again, we consider the 2 degree of freedom RR manipulator. So theta 1 and theta 2, y, x. Okay, we found that the end effector we already found by using the forward kinematics. So at the end effector, what is the x value? So they are this end p end effector x comma y. So the world space coordinator, you know what is x? X equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus theta 3. Okay, this is theta 2. Y equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. This is for RR robo shown here. Suppose if you extend one more link, so end effector P equal to X and Y. At this case, for 3R, for RR robo manipulator x equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus L3 cos of theta 1 plus theta 2 plus theta 3. Similarly, y equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2 plus L3 sin theta 1 plus theta 2 plus theta 3. Let's now differentiate these equations, say 1 and 2, with respect to differentiate 1 and 2 with respect to t. So what happened? We'll be getting dx by dt and dy by dt. Okay. What is dx by dt? Dx by dt, which is equal to x dot. So this can be represented as minus L1 sine theta 1 minus L2 sine of theta 1, sine theta 1 into d theta 1 by dt, into say I'm going to just put theta 1 dot. That is, this is nothing but, so differentiating this L1 cos theta 1 differentiation is actually we are differentiating with respect to x, sorry, t, not x. Okay, so here minus L1 sin theta 1 into d theta by dt, d theta 1 by dt, that is represented as theta 1 dot. So dx dot x dot is, this is nothing but dx by dt, right? So the next is minus sine theta 1 plus theta 2, sine of theta 1 plus theta 2, sine of theta 1 plus theta 2 into theta 1 dot plus theta 2 dot minus L3 sine of theta 1 plus theta 2 plus theta 3 into theta 1 dot plus theta 2 dot plus theta 3 dot. Right. Similarly, for y dash dy by dt is nothing but y dot. So this is minus, L1 cos theta 1 into theta 1 dot plus L2 cos of theta 1 plus theta 2 into theta 1 dot plus theta 2 dot plus L3 cos theta 1 plus theta 2 plus theta 3 into theta 1 dot plus theta 2 dot plus theta 3 dot. So this is x dot and y dot. So this gives the end effector velocity. So say equation number 4. This equation number 3. So the equation number 3 and 4 gives the end effector velocity as a function of force and joint velocity. Okay. So equation 3 and 4 gives the end effector velocity as a function of force force and joint velocities. Junction of force and joint velocity. So this can be rearranged in a matrix format. So x dot y dot, by rearranging this equation, let us form as a matrix. So minus, I am going to simply write in a short format. So L1 sine theta 1 minus L2 sine theta 1 and theta 2, sine of theta 1 plus theta 2 minus L3 sine theta 1 plus theta 2 plus theta 3. Okay, here L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus L3 cos of theta 1 plus theta 2 plus theta 3. So this element is minus L2 sine theta 1 plus theta 2. Better I represent this as in a short form because space is not there. S L2 S of 1 2 into, sorry, minus L3 S 1 2 3 minus L3 S 1 2 3. This okay, this is the third row. This is the second row. This is the third row, right? Similarly, for here, sorry, this is the second column and this third column. So here the second column is L2 C12 plus L3 C123. Similarly, here L3 C123. Here int, okay, int theta 1 dot, theta 2 dot, theta 3 dot. See, if you multiply this this expression, this this first column, this is the second column, this is the third column, this third column. So if you multiply this, see, minus L1 theta 1 minus L2 theta 1 theta 2 theta 3, this into this first element plus this into this second element. So this will be equal to 3 and 4. So we can represent the 3 and 4 like this, right? So what is this? See here, this element is, this element, first row, first column element is nothing but dou x by dou theta 1. The second element is the second column, first element. Okay, so that is dou x by dou theta 2. The third one is dou x by dou theta 3. Similarly, here dou y by dou theta 1, dou y by dou theta 2, dou y by dou theta 3. So this is the velocity joint, the velocity of the frame x dot y dot, right? This resulting matrix is called Jacobian matrix. This matrix is called Jacobian matrix and provide us the mapping from joint space to the whole space, Cartesian space. So this matrix called Jacobian matrix. Jacobian matrix. So this provide with us the mapping from the theta to q to x. mapping this mapping between what is this? Sorry, here I missed with the parameter. That is the mapping. Theta 1 dot, theta 2 dot, theta 3 dot. Okay, theta 3 dot. So what is this? This can be the world space coordinate. So the Cartesian coordinate, say x, y is that. This is equal to, this is the Jacobian matrix. So this is represented J and the Q. This is all Q dot. Q dot. So x dot in general, this is the Cartesian coordinate. This is the joint coordinate. So the Jacobian matrix relates. Okay, it defines, describes the mapping between joint space and Cartesian space. That is world space. Clear? Let's see this the general format for nth order manipulator. This can be written as, for n-link manipulator, the Jacobian representation, say x1 dot, x2 dot, x3 dot, etc., etc., x, say xn dot. So this is equal to dou x1 by dou theta 1. Okay, dou x1 by dou theta 2, etc. Dou x1 by dou theta n. Similarly, dou x2 by dou theta 2, sorry, theta 1, dou x2 by dou theta 2, etc. Dou x2 divided by dou theta n. So similarly, dou xn, xi or xn divided by dou theta n, sorry, theta 1, dou xn by dou theta 2, dou xn by dou theta n. So this is the general representation of the Jacobian matrix. This one is theta 1 dot, theta 2 dot, theta 3 dot, etc., etc., theta n dot. So simply this can be written as x dot equal to the Jacobian matrix to theta dot matrix. Suppose if you want to find theta joint parameters, so very simple. So theta dot equal to Jacobian inverse matrix to x dot. So this is mapping. This is called mapping between theta and x. Clear? So this is called Jacobian matrix. So consider, let us do the 2R matrix. Consider the 2R matrix, 2R manipulator x of theta 1 comma theta 2 equal to L1 cos theta 1 plus L2 cos of theta 1 plus theta 2. Y of theta 1 and theta 2, L2 sin theta 1 plus L2 sin theta 1 plus theta 2. So differentiating with respect to the angles, their angles. So what is dx? Okay, dx equal to dou x by dou theta 1, dou x of theta 1, theta 2 with respect to theta 1 into d theta 1 by dt plus dou x of dou x of theta 1 theta 2 with respect to dou theta 2 into d theta 2 dy equal to dou y of theta 1 theta 2 divided by dou theta 1 into d theta 1 plus dou y of theta 1 theta 2 divided by dou theta 2 into d theta 2, right? So this is the differentiation for the 2R manipulator, 2R two-link manipulator, that is 2-degree of freedom manipulator. Viewing as the matrix in the Jacobian, dx equal to j t theta. Okay. So what is j? The J matrix equal to minus L1. You differentiate this. The in between skipped, right? So if you differentiate this x of theta 1, theta 2 with respect to theta 1. So with respect to partially theta 1. So here L1 cos theta 1 into 1. Okay, into 1, that is d theta 1 d theta by dt, right? So sin theta 1 minus minus of L1 minus of L1 sin theta 1 minus L2 sin theta 1 plus theta 2, theta 1 plus theta 2 minus L2 sin theta 1 plus theta 2. This first element is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. L2, sorry, correct this. L2 cos of theta 1 plus theta 2. Right? So this J can be written as this first column is J1, Jacobian matrix J1, this J2, so velocity profile, velocity equal to J1 theta 1 dot plus J2 theta 2 dot. So this is the velocity matrix, velocity matrix using Jacobian, right? Next is for a small rotation, for a very small rotation, for very small rotation, say del x or del phi, okay, for del phi or del alpha, like that. So for very small rotation, cos of say d phi or del phi, cos of del phi equal to 1, whereas for a small angle rotation sin phi equal to phi, sin del phi to del phi. So this you know, right? For very small angles, even say 0, small 0.1, cos value is 1, cos 0 is 1. Similarly, sin phi, sin small value, sin 0, okay, is a small value, sin of angle, sin theta equal to theta. Sin theta equal to theta for small angle. So that's we are following here. So rotation of x, okay, the rotation of x about for a small angle alpha, d alpha. So what happened? So you know what is x value 1 0 0 0 d alpha, d sin alpha, that is okay, cos d alpha. Cos d alpha minus sin d alpha or del alpha. 0 sin, let us follow d only here. Sin d alpha cos d alpha. So what can you simply replace these values? Cos d alpha equal to 1. So 1 0 0 0 cos d alpha. Cos d alpha is cos small changes equal to 1 sin small changes del alpha. Okay, del alpha. Here 0 del alpha 1. Okay. So this is the rotation of a frame for a small angle. Similarly, please calculate for Ry with respect to small angle beta. Okay, what is the rotation of angle about beta? Cos small angle d beta 0 sin d beta 0 1 0 sin minus sin d beta 0 cos small angle d beta. So cos d beta is 1 0 only d beta 0 1 0 minus d beta 0 1. Similarly, for rotation about z-axis, d gamma. Okay, what is d gamma? So cos d gamma minus sin d gamma 0. Sin d gamma cos d gamma 0 0 0 1. Now again similar to the above equations, let us substitute the value. Cos d gamma is 1 minus d gamma 0 d gamma 1 0. So 0 0 1. So for a, this is called infinitesimal. Okay, for very small rotation call, this is nothing but infinitesimal rotation. This is the technical name, rotation, for very small rotation. Okay, here you can also note that r of x, okay, rx of d alpha into ry. What is rx d alpha? If x and alpha same, rx ry so rx d alpha into r d ry d beta can be r if alpha equal to beta, then r y of beta into r x of alpha. Okay, so if you consider the alpha and beta same equal, then the rx into d alpha, or say d alpha, the ry also d alpha. So in this case, if you multiply this and this, rx and ry, say rx and ry for a small angle, you multiply this and this. So this, if you multiply these two matrix, first rx and ry, then multiply ry and rx, both will be same. So these two are commutative. Okay, commutative. So what is the property of commutative? A cross b equal to a dot b equal to b dot a. So this is commutative. So it obeys the commutative law, right? So inverse Jacobian, we already seen. So what is the purpose of inverse? Finding inverse Jacobian. Inverse Jacobian help us to determine the joint parameters. Inverse Jacobian. Okay. So what is the purpose? In many instances, it is helpful to determine the joint parameters theta dot. That is equal to j theta inverse of x dot. So theta dot. So it helps to determine the joint velocities theta 1, theta 2 dot, theta 3 dot, etc. from the frame velocity. From the frame velocity, we must aware of that. The inverse Jacobian matrix may be uh, undefined or singular. Okay, undefined or singular. The points on the workspace at which the Jacobian is undefined or singularities. Okay, singularities typically occur at the workspace boundaries at interior points. At the interior points where degree of freedoms are lost. When it is lost, so the singularities will be defined. So that's why the singularity is determinant of j equal to 0. So singular for singular solution, right? For singular solution. So for the same manipulator, we know the 2R manipulator for same 2R manipulator, x equation is L1 C1 plus L2 C12. Y equal to L1 S1 plus L2 S12. What is C1 cos theta 1? C12 cos theta 1 plus theta 2. L1 sin theta 1. L2 sin theta 1 plus theta 2. Then for this Jacobian, what is x dot? X dot, y dot we already found, right? This is equal to minus L1 S1 minus L2 S12 minus L2 S12 L1 C1 plus L2 C12 L2 C12, right? So this is theta 1 dot and theta 2 dot. Okay. So this is a Jacobian matrix. Jacobian. So now let us find theta 1 dot and theta 2 dot. What is theta 1 dot? Theta 1 dot and theta 2 are the joint velocities. So joint velocities. So this can be found from the J inverse. So Jacobian inverse matrix into x1 dot, y1 dot. Okay. X dot and y dot. X dot and y dot. So what is J inverse? So J inverse equal to, let us find the inverse matrix for this. So this is find the inverse matrix from the matrix. What is this matrix? So what is the inverse of 2 by 2? So 2 by 2 matrix equal to 1 by determinant of 1 by determinant of 2 by 2 matrix. Okay, just exchange the left hand side. Okay, what is the left diagonal? This diagonal we have to exchange the parameter. So this would be here. That is called adjoint matrix of 2 by 2. So we have to interchange this diagonal and sign change of this diagonal. Am I right? So what is L2? L2 cos 1 2. Okay. Then sign change of this minus L2 sin theta 2. So plus, it becomes plus. So L2 sin 1 2. So here minus L1 C1 minus L2 C12. Here minus L1 sin 1 S1 minus L2 sine 1 2. So this is adjoint matrix. Okay, so adjoint 1 by, what is the inverse matrix? A inverse matrix equal to 1 by delta determinant value of adjugate matrix, adjoint of A. So for 2 by 2 matrix, very simple, we can interchange this rule, right? So J inverse 1 by delta L2 cos theta, this thing. So what is determinant value of this? Please do it. So multiply this and minus of these two, right? Multiply. So you do it. What is determinant? L2 cos 1 2 into minus L1 S1 minus L2 sine of 1 2 minus L2 sine 1 2 into minus L1 C1 minus L2 C1 2. So what is delta? So you will be getting L1 L2 L1 L2 sine theta 2. Please do it and tell me the intermediate step. Very simple manipulation. Okay, what I am getting is L1 L2 sine theta 2. Okay, sine theta 2. So it is clearly shows that, so as theta 2 approaches to 0 or 5, as this clearly tells, as this theta 2 approaches 0 or 5, 0 or 5, the manipulator becomes, this manipulator becomes singular. See what it tells. Say this is theta 1. Okay, so theta 2 is here. When theta 2 value is 0 or 5, okay, either theta linked to L2 is this side, say L1, L2 also this side, or the L2 is this side. The theta 2 value is 0, this becomes singular, okay, because the determinant of J equal to 0. Okay, so J or J inverse equal to 0, then it is singular. Clear? So then we can also use the Jacobian to compute the joint torque. So the same Jacobian matrix also used to determine the static forces. Also used to find the static forces. Jacobian also used to determine the joint torque required to maintain the particular force at the end effector when it is gripping or grasping, to maintain the joint torque. Okay, particular force at the end effector. Consider the concept of virtual work, that is work done equal to force into distance, del x equal to, so this is a linear force into the perpendicular distance. Okay, so that is torque into d theta. Okay, dou theta or d theta, or force translational dou x equal to tau translational, that is into dou theta. Okay, earlier we saw that dou x equal to j dou theta. Okay, dou theta or del theta, right? So that f translation equal to of j equal to tau translational, similar to the x and world space coordinator and the joint parameter. This can be written, or tau equal to j translational transpose into F into F. So this is based on Jacobian. So one more dynamics defined by the Euler. So Newton's Euler. So he suggested Newton Euler method. What he suggested is we can analyze the robot dynamics using classical Newtonian equations. What is classical Newtonian equation? Sum of forces equal to mass into accelerations. Similarly, sum of torque equal to Jacobian into d double d square theta by dt square. So this can entail the iteratively calculating the velocities and acceleration for each link. So and then computing the force and the moment balances. What is moment balance? Force into distances. So this is moment balances. Okay, moment force into distances. Moment balancing in their system. Alternatively, closed loop solutions can be exist for a simple configuration. So finally, from this robotic dynamics and kinematics discussion, okay, this was the important point. Kinematics is the study of motion without regard the forces and their creativity, right? So kinematics deals with the structure without force, okay, without force. So the study of dynamics allows us to understand dynamics, right? Dynamics used to help us to study to understand the forces and torques which acts on the system and result in motion. Okay, so basically it's a motion dynamics. Motion mainly allow us to understand velocity, acceleration, and forces and torques. So understanding these motions, the required forces is essential for designing a robotic system. They're very essential for robotic system. Thank you.